Ever wondered how data is transferred in your computer systems? It's a process that's both intricate and fascinating, and it all hinges on the use of codes. In the realm of computer systems and communication, these codes are the essential methods by which we represent information for transmission, storage, or processing. The two predominant types of codes you'll encounter are parallel and serial codes. Parallel codes transmit multiple bits simultaneously, making for rapid data transfer but requiring more physical connections. On the other hand, serial codes transmit data one bit at a time, which is slower but requires fewer connections and is less prone to synchronization issues. Throughout this video, we'll delve deeper into these two categories, exploring their advantages, disadvantages, and practical applications. It's a journey through the unseen highways of data in our computer systems. So, are you ready? Dive in to explore the fascinating world of parallel and serial codes. Imagine a highway with multiple lanes. That's how parallel codes work. Parallel codes in the realm of computer systems and communication are akin to multi-lane highways. They transmit multiple bits of data simultaneously along separate lines or channels. Imagine each lane of a highway carrying a different car at the same time. Similarly, in parallel codes, each line carries a different bit, resulting in faster data transfer. This method of data transmission is recognized for its simplicity in design and understanding. It's like understanding that more lanes on a highway mean more cars can travel at the same time. However, just as a multi-lane highway requires more resources to build and maintain, parallel codes require more physical connections or wires for transmission. This can increase complexity and cost. Moreover, there's a potential hitch with synchronization. Imagine if some lanes on the highway are smoother than others, causing cars to reach their destination at different times. In the same vein, differences in signal propagation times can lead to synchronization issues in parallel coding. A real-world example of parallel codes in action is parallel ATA or PATA cables. These are used to connect hard drives and CD/DVD drives to a computer. The parallel transmission allows for quick data transfer, but the need for more wires and the potential for synchronization issues are trade-offs to consider. In summary, parallel codes are a bit like our multi-lane highway. They allow for speedy data transfer and are relatively simple to understand. However, their need for more physical connections and potential synchronization issues mean they require careful handling. Despite these challenges, they continue to play a vital role in areas where high-speed data transfer is paramount. Parallel codes, though simple and fast, require more resources and careful handling. Now picture a single-lane road. That's the essence of serial codes. A serial code, in essence, is a bit like that single-lane road, transmitting data one bit at a time over a single channel. This straightforward approach may seem slow, but it has its advantages. Firstly, serial codes require fewer physical connections. This reduction in complexity not only cuts costs but also decreases the potential for errors and technical issues. Just think about it. Fewer connections mean fewer things that could potentially go wrong. This simplicity is a significant advantage, particularly in systems where reliability is key. Another advantage of serial codes is their suitability for long-distance communication. Unlike parallel codes, which can suffer from synchronization issues over long distances, serial codes maintain their integrity, regardless of distance. This makes them an excellent choice for systems where communication needs to span considerable distances. However, there's no such thing as a free lunch, and serial codes come with their own set of disadvantages. The most significant of these is their slower data transfer rates. Because they transmit data one bit at a time, serial codes can't compete with the speed of parallel codes, which send multiple bits simultaneously. But where might you encounter serial codes? Well, they're more common than you might think. The Universal Serial Bus, or USB, which you use to connect various peripherals to your computer, operates using serial codes. Serial ATA, or SATA, which connects storage devices like hard drives and SSDs, also uses serial codes. Even the Ethernet cables that provide network communication rely on these single-lane roads of data transmission. So, while they may be slower, serial codes offer cost-effectiveness and are excellent for long-distance communication. They're the tortoise in the race against the hare of parallel codes. And as we all know, sometimes slow and steady does indeed win the race. Serial codes, while slower, offer cost-effectiveness and are excellent for long-distance communication. Line codes, they are the voltage levels that represent our data. Line codes are a special type of code used in digital communication to represent data as electrical voltage or current levels on a communication channel. They are, in essence, the bridge between our digital data and its physical representation in the real world. There are several types of line codes, each with its unique way of representing data. First, we have unipolar line codes. These use a single voltage level to represent data. It's simple. Either you have a voltage present, indicating a 1, or there's no voltage, indicating a 0. It's as straightforward as it gets. Next, we have polar line codes. These are a bit more complex, using 2 voltage levels to represent data. One level is positive, the other is negative. This dual voltage system provides a bit more flexibility in how data is represented. Then there's the Manchester line code. This one is a bit unique, as it combines voltage transitions to represent bits. This means that the actual transition from one voltage level to another is what signifies a 1 or a 0. We also have NRZ, or non-return to zero line codes. These use 2 voltage levels, with one level representing 0 and the other representing 1. The key characteristic here is that the signal doesn't return to a 0 voltage level between bits. Lastly, we have RZ, or return to zero line codes. These are similar to NRZ, but with a key difference. In RZ line codes, the signal returns to a 0 voltage level at the middle of each bit period. This can help reduce errors in data transmission. Each of these line codes has its own advantages and disadvantages, and the choice of which to use can depend on a variety of factors, such as the specific requirements of the communication system, the type of data being transmitted, and the physical characteristics of the transmission medium. Line codes are the bridge between our data and its physical representation on the communication channel. But what happens when errors occur during data transmission? Enter error detection and correction codes. These codes are like the vigilant guardians of data, adding additional information such as parity bits, checksums, and error-correcting codes to our data. They keep their eyes peeled for any errors that may occur during transmission, and when they spot one, they don't just raise the alarm. They also have the ability to correct these errors. Let's take a closer look at a few examples, shall we? First up, we have the parity bit. This clever little bit adds an extra bit to the data to make the number of ones or zeros either even or odd. It's like the bouncer at a party, ensuring there's always a balanced crowd. Next, we have the cyclic redundancy check, or CRC for short. This method computes a kind of digital fingerprint, a remainder that is appended to the data for error checking. If the fingerprint at the receiving end doesn't match the one sent, you know there's been an error during transmission. And then we have the Hamming code. This method adds redundant bits to detect and correct errors. It's a bit like having a proofreader for your data, catching and correcting errors on the fly. These codes are not merely optional extras, they play a pivotal role in the design and functionality of communication systems. They ensure that our data transfer is not just fast, but also reliable. They make sure that what is sent is exactly what is received, maintaining the integrity and reliability of our data. So while the choice between parallel and serial transmission might depend on factors such as data transfer speed, cost, and specific requirements of the application, error detection and correction codes are always there in the background, silently doing their job. Error detection and correction codes are the unsung heroes, ensuring our data is accurately received. So, parallel or serial? The answer isn't as simple as one might think. To recap, parallel codes transmit multiple bits simultaneously, offering faster data transfer, but require more physical connections and can suffer from synchronization issues. Serial codes, on the other hand, transmit data one bit at a time, needing fewer physical connections and being less susceptible to synchronization issues, but with slower data transfer rates. Then we have line codes representing data as voltage or current levels, with different types like unipolar, polar, Manchester, NRZ, and RZ. Lastly, we can't forget about error detection and correction codes such as parity bit, CRC, and Hamming code, adding extra information to detect and correct any transmission errors. Whether you choose parallel or serial ultimately depends on your specific needs, including data transfer speed, cost, and application requirements. Next time you plug in a USB or send an email, remember the complex codes working behind the scenes to make it all possible.